Hello and welcome back to my favorite people. And as usual, thank you very much for watching this lecture video. If you take an OH, attach it to a carbon atom, in that case, we say we have an alcohol functional group. But if O is bridged between two carbon, in that case, it will be ether molecule or ether functional group. Now, we saw that we can use the alcohol and react it with a carbonyl group, and that's gonna give us hemiacetal or acetal. It depends how many alcohol molecule we use. If it's just one, it will give us a hemiacetal. If we use two of them, in that case, we will get acetal molecule. Now, right underneath of oxygen, I have sulfur, and I know oxygen. It comes with two lone pairs, and so oxygen is attached to one hydrogen and one carbon atom. And again, I said right underneath of it, I have sulfur. If I take a sulfur and attach it to one hydrogen and other side attach it to carbon, in that case, we say we are dealing with thiol functional group. And a thiol functional group should be able, to run similar chemical reaction like alcohol with carbonyl group. And I want to actually go after those. Before I practice some example, I have to say this. If you take a sulfur, attach it to carbon atom, and that means you take one of the hydrogen, replace it by methyl group or any carbon, you will get sulfide functional group. Okay, so we're talking about chemical reaction of thiol group or thiol molecules with carbonyl. And if I take two molecules, two from thiol, and react them with a carbonyl or aldehyde, it will give me thioacetal. This is exactly similar to the acetal. And acetal, we had the OH. We had the OH, we had the OR instead of, SR, and we had the two of them. Okay. If you replace sulfur oxygen by sulfur, in that case, we say you got thioacetal plus water molecule. And I can run this reaction with diol instead of, alcohol, and that's going to give me a cyclic acetal molecule. Now, we can practice similar thing, but this time instead of using diol, we can use thiol and practice the same chemical reaction, and that's going to give us a cyclic thioacetal. And if you remember, we said cyclic acetals are stable, and in fact we can use them to protect carbonyl functional group. So this one, it will be cyclic acetal. And you can practice the same thing by using sulfur instead of oxygen, and that's going to give you a cyclic compound. And but there is one actually benefit in it, and the benefit is like if you take cyclic thioacetal and treat it with raining, nickel and catalyst, you can actually get alkane. That means you can saturate it in a carbonyl group and turn it to alkane. And this is going to be then like the example that I will practice. So I have a ketone and like a carbonyl group, and I'm treating it with H plus and dithiol. And why H plus? Because I want to activate, the carbonyl group. And so first step of this reaction, we're gonna, technically the oxygen will go after H plus, and it will give us such a compound. Now I will have only one lone pair, and there is a positive charge there. So that means the carbon that I'm going to highlight, this carbon is going to be is going to have a huge positive charge there, and because we know oxygen is more electronegative than carbon, so it will pull electron density, and it will create a huge positive charge there. Now time to have the nucleophile, and the nucleophile it can get inserted and get attached to carbon. Okay, and so what do I get? I get this intermediate. I'm going to write the final intermediate. I will get something like this. And next step, I'm going to treat it with nickel catalyst. And when I run this reaction, I need to use hydrogen gas, and I need to use also heat to run the chemical reaction. Let's talk about the catalyst. What's the catalyst? The catalyst is a 50% and an alloy of nickel and aluminum. And we know one thing, that's aluminum. If we take aluminum and react it with sodium hydroxide while we are applying heat, aluminum is going to react with sodium hydroxide, and it might give us something like this. So you might say, why do you add sodium hydroxide and also heat to the catalyst? Because that's going to ruin the catalyst. Okay, and so what's the purpose of having aluminum? Instead of the reaction is going to happen on nickel surface. So imagine you have such a surface, and on this surface you have a bunch of, let's say, circles here. Those circles are nickel. So we're going to say we have nickel atom there. Now your substrate, okay, whatever you have. So I'm going to say, let's say our molecule reactant it's supposed to attach to those nickel atoms. And next, I'm going to also add hydrogen atom, and the hydrogen atom, let's say gas. So the hydrogen gas technically it will break, or hydrogen molecule will break, and they will give me hydrogen atom. So now I will have hydrogen atom attached to the catalyst. And because both reactant and both reactants are close to each other, and both of them are attached to the surface, very soon they're going to find each other and they will have interaction. Okay, those two, they will have interaction, and that's going to speed the reaction. So everything is happening on the surface of the catalyst. Again, still, I did not get the answer. Why do I have aluminum? Why do I need to have aluminum? Okay, let's watch it like this. Imagine you take 10 grams from the catalyst. This is your catalyst. Okay, so that's going to be the catalyst. Now, my molecules, or like reactants, can only reach the catalyst through the surface. So what does it mean? It means whatever inside of that, like spherical object, they will not be accessible. Okay, in order to make it accessible, what we're going to do, we know we have aluminum and nickel there. So we have aluminum and nickel. Nickel is not going to react with sodium hydroxide, but aluminum is going to react. And if aluminum react, this is going to happen. I will get a bunch of tiny holes there. Okay, I get a bunch of tiny holes there, and it gives the molecule, like for example, hydrogen gas, or the reactant, any reactant that I have, it gives a chance actually to diffuse through the catalyst. So the purpose of having sodium hydroxide plus heat is to make the catalyst fluffy, and it will be really fine powder and fluffy powder, and then my gas or my molecules also can get inside that catalyst, and they will get activated, so the reaction will be faster. Now, if I treat it with hydrogen gas, the final product will be this one. And the center I have here, that's gonna technically give me, it gets 2 hydrogen. And now what will happen with the sulfur atom? The sulfur atom will recover their hydrogen, and then they get hydrogen atom again. And so we managed actually to get it back. And so as you see, the carbonyl group got saturated, and now we have a CH2 there. Now, I can switch to another nucleophile, and this time, like I can use hydrogen nucleophile instead of sulfur, and saturate, the carbonyl group. And for this purpose, we can use lithium aluminum hydride, or we can go with sodium bore hydride. What's the difference between lithium aluminum hydride and sodium bore hydride? So write this one. When it comes to lithium, say this one is a strong reducing agent or reductant. This one will be mild reductant or reducing agent. That's the difference between them. That means when it comes to lithium aluminum hydride, you can use it for carbonyl group, or you can also use it for an acid, or like for example, an ester group, and reduce that one. Well, for sodium bore hydride now is not that strong, and so you can't really expand it that far. Okay, let's practice some example about it. What will happen if I start with aldehyde or ketone and run such a reduction reaction? Okay, so I'm going to practice 2 examples. And the first example here, I have a ketone, and on my ketone I can see a methyl group, and other side I have an ethyl group. So we have ethyl, and this one is methyl group. Now, when you run the reaction, and a reaction is going to give you H minus, or it's going to be your nucleophile, and the nucleophile, it can be added from the top of the carbonyl group or the bottom of the molecule. So what do I get? I get this. Okay, I got two substituents attached to the carbonyl. Now I will get O, and other side I will have also H. Okay, now I need to neutralize this one as soon as possible. If there is an acidic H there, and O, it will take the acidic H, and in this case we have water. It will go after water, and very soon it will give me this compound. So this hydrogen came from water, while that one came from lithium aluminum hydride. Okay, now I got carbon center that it has 4 different substituents. It means that I can have these two enantiomer. Okay, in one case, maybe OH is facing to us, while hydrogen is back of the molecule, or I might get this one. Let's say, oh, the hydrogen is facing to us, while OH is back of the molecule. Okay, first one, that's going to be 1, 2, 3, and that one is the 4th priority. So I have S configuration. Next one, I get 1, 2, 3. It's supposed to be S, but hydrogen is facing to us, and the 4th priority is facing to us. So we're going to flip it to R. Now, what's the relationship between number 1 and number 2? Those two are enantiomer. So I got 2 enantiomers. Okay, I started with ketone, and I got an alcohol. Now, Mike here, I said I started with ketone and I got alcohol. If you look at the alcohol that we got, our alcohol is a secondary alcohol. Okay, we have a carbon that's attached to two carbons, and there is one OH sitting on it. Okay, from ketone we got a secondary alcohol. Now, what if we start with aldehyde? And again, I can use any of this reducing agent, and at the end quench the reaction by acidic solution, and I have an aldehyde this time. There is also double bond there, and what else? I have a chiral center, and my chiral center, if I go after after the chirality, this is going to be 1, that one it will be 2, and this one 3, and hydrogen it will be the 4th one. So I go 1, 2, 3. This one is going to be R configuration. Now, if we use reducing agent, it's similar to the ketone, it will give us it will give us an alcohol, and we will get such a thing. So I have a chloride here, hydrogen is there. Now I will get O, H. I had hydrogen before, and what did we add? We added hydride. Okay, we added hydride. So I'm going to add the hydrogen here. Now, this center, it has 2 hydrogen attached to it. So that's not a chiral center. Okay, we did not create a chiral center. Now, we started with aldehyde, and the alcohol that I got is attached to only 1 carbon. So that's going to be a primary alcohol. Okay, primary alcohol, because my carbon is a primary carbon. So the difference between ketone versus aldehyde. If you take a ketone and reduce it by a reducing agent like lithium aluminum borhydrate, or lithium aluminum hydrate or sodium borhydrate, you will get a secondary alcohol. If you start with aldehyde, you will get a primary alcohol. And now, one thing that I want to actually highlight, nothing happened to the double bond. Double bond stayed as it is. Okay, so those reducing agents will not touch the double bond. They will only go after the carbonyl group. Okay, and this is going to be the end of this lecture, and thank you very much.